Good morning. Welcome everyone to our lecture this morning. Before we get started, I want to share uh, two data regarding the homework and the quiz, which was due last night. And then, we will have a feel of where we are. I want to start with the homework, and what you think. You will see yourself. Let me see homework or homework assignment. This is, you know, why I'm bringing this to you is so that we compare with the results or the statistics for the quiz, and this will translate to how we will do in the midterm exam and also the final exam for the course. If you look at what you are looking right now is the number of students who completed the homework. I know it is due on the 20th. That is chapter 4, reaction in aqueous solution. And what you see here, out of 113 students, only 22 have either attempted or they have complete, which is 98, an average score of 96.8, which means if we use the homework to prepare ourselves, we should get the same score in the quiz, all right? And also the midterm. So, which means somebody or somewhere is going to take the quiz before completing the homework, and which means chances are they will also take the exams before completing the homework, before completing the quiz. And chances are maybe somebody is not even attending the SI session, and it will affect or impact your final grade as well. So please take seriously the homework assignment. I can look at the how long somebody you want to see your own score, how you are doing. Please let me know. So this is not really impressive from my perspective. 22 students completed the homework before the quiz. Please try to uh, complete the assignment. I know I give you time to do that. Please step up the game. Let's shift gears to the quiz, which was due last night. If you look at the average score compared to the quiz, why is the quiz 77%? The average score is 77%. And I can tell you from where I am that probably this score has to do with majority of folks not doing the homework before taking the quiz. All right, let's drop down this way. I want you to put more effort in completing the homework, and then how we will see how this average in the next quiz will look like, and how compared to the first exam. Today I don't want to, all right, today I don't want to pull the practice homework assignment. Remember, I always prepare the practice homework assignment. We do not affect your final grade. You can just use to practice that and see if the numbers really make sense. If it did, if I have justification why I should prepare also, the practice assignment. All right, I'll look at that, and maybe next on Thursday I'll show you more data on that. All right, so that is where we are. This is the average score for the quiz. Please continue working. Whole homework are available. If you look at majority, we are down here, which is good for those who did the work, except we have few down like 20%, and so folks who are down here maybe fall under the 113 or out the 22 we didn't do the homework, and they just dump it or jump onto the quiz. So let me just before we move on to chapter 5, thermochemistry. I want to wrap up chapter 4. There was one question which was missing a file, and I promised to cover that. This was on the learning check on the PowerPoint slide. Let me pull chapter, no, this is chapter 5. All right, chapter 5. All right, let me go to 4. Let me go to 4. But before we do that, this is the question I wanted to go over. There was some missing information. Jennifer, you have a question regarding chapter 4. Please, vocabulary, tell us if it is a titration or dilution. All right. In the conceptual question, all right, Jennifer, to clarify your question, I think you want to distinguish whether it is dilution or it is titration. Problems. Let's say you are given a math space problem, you don't know whether to use the dilution equation. I'll say that you got to use critical thinking by looking at the information given. For example, in dilution, you'll have only maybe one molarity, and then you are asked to find, when this solution is diluted from this to this. All right, what is the final volume? All right, what is the final concentration, or what is the final molarity when you take this and that, assigning M1, M2. That is what? That is the dilution. I will use the information given. In dilution problems, you will be given one molarity and you are asked to find the second molarity or final molarity or initial volume and then final volume. So you'll have 4 identities in dilution equation. Well, titration means, generally titration is basically the type of, it falls under the type of reaction, aqueous reaction we talked about, and that is acid-base neutralization. Most problems in titration involve acid-base what? Acid-base neutralization, which means you will have 2 reagents. I'll see this is a base, this is an acid. So it's assumed that you already know that this is an acid. You should be able to classify a reagent and an acid and a reagent as a base, so that when you combine or neutralize, you know this is what it is. So for titration problems, you'll have 2 reagents. That's the only way I can look at it, to differentiate titration problems from the dilution problems. And also practice with this, you will know, doing the problems on titration and doing the problems on dilution, you'll have a sense that this is a dilution problem. Words such as a solution is diluted to, underline the word diluted, all right? If the solution is diluted to, then you know this is a dilution problem. A reagent is titrated with, that means it is titrated with that. Neutralization, maybe going back to what I do have here, which I may use it to further explain, all right, the difference between neutralization and dilution. If you look at problem A, to come up with that, this was end of chapter problems. This was end of chapter problems in the lab manual, and not lab manual, but the text. All right, I think it was number 80 on page. I do have this was number 81. It is number 81. This problem is number 81 in the lab manual, page 158. When I read last time, there was something missing. All right. There was something missing on problem number 1. And this has to do with the volume. If I change that, all right, to neutralize 50 ml of. So here to neutralize 50 ml of. So we know the of volume of the volume of 50. This is 50 ml of 0 0.0875. This is molarity. M stands for molarity NaOH. The volume of 0, that means we are reacting 0.115 molar HCl. So this should read this problem here. By the way, page 158, number 4.81 in the text. So the volume for the base here is NaOH. So if I look at this, all right, it is acid-base neutralization, acid-base neutralization. And if you write the equation, H, all right, Cl4, chlorine aqueous plus NaOH aqueous. In acid-base neutralization, always H2O is produced. It's one of the product. So H2O liquid plus the salt, sodium hypochlorite, ion. There is the exchange of what? Exchange of ions, switching of ions by the cation. So if you look at this, you should be able to write a balance. This is acid-base neutralization. There is an acid, there is a base. The equation has to be balanced. Let's see if the equation is balanced. So if we have here 1, we have here 1, so it is 1 to 1 to 1. If you look at the number of hydrogen, 1, number of oxygens, 5 on either side, so mole ratio is 1 to 1 to 1. Mole ratio is 1 to 1 to 1. So you write down what we have for each reagent. Sodium hydroxide molarity is 0.0875. Volume in liters, you got to change the volume in liters because change the volume to liters because of what? Molarity is always volume of solution in liters. So I change this to 0.050 liters. What we know for oh yes, thank you, Tony. You are asking where did I get the 50 ml? It is missing in my PowerPoint slide here. When I did last week, I promised to come back here. I said there's something missing. When I went back to where I got this problem, 50 ml is missing here to neutralize 50 ml of 0.0875. So the question should read, what volume of 0.115 molar HCl4 solution is needed or required to neutralize 50 ml of? So this is where the 50 ml came in. You want to revisit, look at the problems, page 158, number 81, 4.814, meaning chapter 4, and 81 is the problem number. That's where I'm getting the 50 ml. it was missing here. So it is neutralized 50 ml of that. Thomas, we are on the same page? Say yes. Thank you, sir. Oh, yeah, Tony, thank you. So here, how I approach the neutralization reaction, I write the information I have for one reagent, Ploid, once I balance the equation. And for the second reagent, what we know here is molarity is 0.115. This is the molarity. Do we know the volume? And remember, the volume has to be in liters. This is the question mark, because the question is, what is the volume? So I don't know the volume. Number of moles as well here. I don't know the number of moles. Number of moles equals to question mark. But this is now where you need to think that from the balanced equation, you should be fast in synthesizing the information that what are the coefficient in the balanced equation tells us. It's the mole ratio. It's the mole ratio. So since I have, for the acid, I have two unknowns. For the number of moles for the base, I can find out using the molarity equation. Remember, molarity equals to number of moles, all right? Number of moles over volume in liters, which means number of moles of NaOH is given by the molarity of NaOH times volume in liters of NaOH. Do I know the volume? Yes. Do I know the molarity? Yes, this is the molarity, and 50 ml was given in the problem. So I'll just plug in the equation here. Molarity is 0.0875. Remember, molarity is the same as moles per liter. Capital M is the same as moles per liter. It's another unit. Times the volume in liters, 0.050 liters. So that liters and liters will go. Molarity is the same as moles per liter. So with this, we can now determine the what? 0.0875 times 0.0550. And I have 0.004375 moles of NaOH. These are moles of what? NaOH. Moles of NaOH. I had to find the number of moles of NaOH from this equation. It is 0. So we know now the number of moles, 0.00435 moles. So what I need to do is find out, all right, the number of moles of the acid. From the mole ratio, it is 1 to 1, okay? 1 to 1. So if I know the number of moles of NaOH, the coefficient in the balanced equation is basically to tell us the mole ratio. If you know the number of moles of this, you can use the mole ratio to determine that. If you want to see how you proceed with that, it is just using the mole ratio 0.047, all right, 43. This is 4375 moles of NaOH times, now what you see here is I'm looking for moles of AClO4. Here is moles of NaOH. This is 1 to 1 mole ratio. from the balanced equation. Mole ratio from the balanced equation, which means moles of NaOH will cancel with moles of NaOH. So we have the same number of moles. That's to show you how to find the number of moles of acid using the mole ratio, using the mole ratio. I'm using the mole ratio to find what? The number of moles of the acid. If you look at this question here, what volume? So if I know, or if we know the number of moles of the acid is the same, 7.5 moles. I'm just writing above it so that I know the information. If I know the molarity and I know the what? The number of moles, I can find the volume. I can find the volume. From here, volume in liters of HClO4 equals to number of moles of HClO4 over molarity of HClO4. Showing your work. So we know the number of moles 0.004 of molarity 0.115. This will give you more volume in liters. That's why I have the subscript liters in there, divided by 0.115. Divided by 0.115. So this leave or give us 0.03804 this is liters, and you can change to what? To milliliters by multiplying per 1,000. This is the same as 38.0 ml. Just rounding it off. So this is a titration or neutralization, not necessarily titration. For the titration problems, you will cover in details in Chem 2, but you have to be well-rounded in neutralization reaction. Mole ratio. Knowing the correct formulas of your acids and bases, it's gonna come back again in Chem 2, neutralization, balancing the equation. They will not teach you how to balance the equation moving forward. They will have expected you that you learn how to perform calculation involving neutralization. Any question on number one? I promised to start off with that. All right, let's see the follow-up question. Lauren brought to my attention, and I want to recap again question 2. Any question on question 1? If there is no question, I will, I know, yes, I will unlock for you, Lauren. I will unlock for you the quiz. And Thursday, if you have any question, I don't want to, just I will unlock the quiz on Thursday. I will spend maybe a few minutes, or you can come see me during office hours or any other time convenient to you to cover your quiz, or you can use the SI session also to go through why you missed. Once I unlock the quiz for, you should be able to see what went wrong. Okay, you start to study for the exam, coming exam. Thank you. So yeah, I'll take care of that, Lauren. So let's move on to question 2 one more time. What volume of neutralize, that means it's reacting. We did this last time, all right? I know we did this last time, that the reaction is between HCl. This is the same problem on page 158. Magnesium hydroxide. And somebody has a question, I had a question here. Let's see. This is acid-base neutralization. Neutralization, neutralize, underline the word neutralize, that means H2O is produced. So one of the product is liquid H2O. If you are wondering how it comes, I know one of the product is liquid H2O is based on the understanding that always acid-base neutralization produce H2O. And I'm using the crossover rule to predict and write the correct formula. And an salt here is magnesium. It is not MCl like that, but you have to play with the rules. Crossover rule, magnesium is in group 2, has a charge of positive 2. That is the correct formula for magnesium chloride. And it's soluble in water. You have to use the solubility rule. Now, once you write the correct formulas of your desired product, it wouldn't matter if you are using the right equation in calculation. If you don't balance the equation, you will get it wrong. So we need to balance this equation that on the reactant side, we have 3 hydrogens. So we need a 2 in front of HCl so that we have what? 2 hydrogens and 2 hydrogens make it 4. That means we need a 2 in front of H2O to make the number of hydrogen equal the number of chlorines, 2 on either side, magnesium 1 on either side. So the coefficient for magnesium chloride is 1, magnesium, for magnesium hydroxide is 2. Last time I used I derived the net ionic equation, or try to derive the net ionic equation, but at this point, you can just use the molecular equation the way it is to find the moles of each reactant in the equation. Work both ways. Somebody asked last time, and I say you can either, that will work too, so long as you know what you are doing with the number of moles. So I recommend just use the molecular equation, which is the way it is right now, which tells us the mole ratio is 2 to 1 to 2 on the product side to 1. This is product side, and this is reagent side for the reactant. So HCl, we want to know the volume of HCl. We know the molarity of HCl. To neutralize grams of 2.87 grams of magnesium hydroxide. Unlike the first problem, we had solution here, but here we have a solid reactant. If you try to let this say, oh, I was given, in neutralization reaction, I will always be given molarity, and I'll just go the way it is. But suppose you are given a solid, how do you navigate the problem? You need to know, which I know we covered before, or you should know that there are two equations for finding the number of moles and know when to use which one. Equation one for finding the number of moles, when you are given mass of the solute, is gonna be mass in grams over molar what? Molar mass. So I'll give you this, or if not, this one right here, if not given, sometimes given, sometimes not. If not given, use the periodic what? Periodic table. Use the periodic table to find the molar mass. And if you are given the mass, then you will get the what? Get the number of moles. Where we are going with this is we want to know the moles of magnesium hydroxide, which is solid in this case. This equation will not work. Equation 2 here, you may get stuck trying to use this equation, molarity, all right, molarity times volume in liters of solution, volume in liters of solution. So you got to know when do I need or when do I use this equation? It's based on the information given. Is based on the information given. So with problem 2 here, I will rule out equation 2. This is the right equation we will use to find the number of moles. And last week, all right, we did the calculation. The number of moles of NaOH was what? Molar mass was 58.319, 58.319, 58.319. So if I want to find the number of mole of magnesium hydroxide, it's gonna be 2 point what? 87, or rather, if you want to really see how to reconcile the unit, 2.87 grams of magnesium hydroxide times the molar mass as a conversion factor, 1 mole of what? 1 mole of magnesium hydroxide of 58.319 grams of MgOH2. Just to show the setup, somebody might be like, how do we move from here? If you really want to see where you're going, so that you cancel grams, you remain with moles. You remain with moles. So with that, we can just divide that. I just wanted to plug in there, but somebody might get stuck and say, how do we navigate from here to here? 319, and here is 0.0492 moles of magnesium hydroxide, too, like that. So I know what the moles. Remember, if we didn't use the molarity, it's based on the information given. We had to use the equation 1 for finding the number of moles. So that once we know the number of moles, we can use the mole ratio here, that the number of moles here is 0. What? 0.0492. All right, moles, which means mole ratio is, if you look at here, mole ratio is 2 to what? 2 to 1, which somebody last time said, do we use the mole ratio? You don't need to stand around, you don't need to solve the net ionic equation. So if we multiply this by 2 to get the number of moles, all right, 0.0492 times 2, because of the mole ratio, 984 moles of HCl. I know the moles of HCl I needed to completely neutralize that. So if you look at now the information you have, we know the number of moles, we know the molarity of HCl, 0.128. We know the molarity, we know the number of moles, volume, all right? Volume in liters for HCl is given by what? Maybe just erase this mole ratio, we are done with this, so that volume in liters is given by number of what? Moles of molarity. Number of moles of molarity divided by 0.128, which is 0.0984 of 0.128. This is liters. This is liters right here. We use the mole ratio. If we solve the net ionic equation, you gotta be know what you're doing. So right now you can just use the mole ratio, 2 to 1. If it is 1 to 2, whichever way you look at it, it will come out. What I want to point out is always look at the problem, write down the information so that you see which equation is appropriate for what step. All right. I want you to use end of chapter problems on titration and neutralization reaction as well as dilution equation. It will be so clear. All right. It will be so clear which equation you will need. I'll give you all the information, just like exam 1. You'll have the formula sheet. All right. You'll have the constants if need be, but you need to know which equation you are going to use. So I don't want to spend more time on chapter 4. What I want to do is go to chapter 5. If no question, I'll go to chapter 5. We are going to shift gears to something new. We are going to look at something new today. We will shift gears a little bit from what we have been looking all along in chapter 1, chapter 2, chapter 3, and chapter 4. All right. I'm just going to reset this so that I can share my screen. Somebody had requested this to be a little bit larger. Let me just see if it's gonna work. Yes. This is something new today we are going to talk about, and this is the chemistry of something we don't see. In chapter 1, chapter 2, chapter 3, chapter 4, it was about something we can see about matter. There is, to really understand the chemistry behind or around the world we live in, there is one important aspect, and this is the energy. It is totally different from all the chemical reaction we talked about, all the chemical terms. It had to revolve about something we will, or we can touch, we can see, but energy we cannot touch, we cannot see. So in chapter 5, we will look at the thermochemistry which involve energy, and we define energy elsewhere, all right? And there are two types of energies important in chemistry: kinetic energy and potential energy. That will come again in chapter 6. So thermochemistry, to break down or define the term you see on the screen, thermochemistry, all right? This is a study of chemical reactions produce or release absorb energy, chemical reaction that is accompanied by. This chapter fall under thermodynamics. It is an introduction of Chem 2. You will cover in details thermodynamics, which is the study of. It is a branch of thermodynamics right here. This thermochemistry is a branch of thermodynamics, which is basically a study of energy and its transformation to be transformed, the study of energy and its transform. It can be transformed from one form to another form. There is a chapter on its own in Chem 2, and in Chem 1, you know, Chem 1, Chem 2, that means it's a continuation. This thermochemistry falls under thermodynamics. In chapter 5, this is the roadmap which we will follow till the end. Section 5.1, the nature of chemical energy. You see the word energy is in there. We define energy as the ability to do what? Ability to do work. There are 3 laws of thermodynamics, all right? First law, we will look in section 5.2, first law of thermodynamics. The other 2 you will cover in Chem 2, second law of thermodynamics and third law of thermodynamics, but we'll just look at first law, which is something you already know. Enthalpy of reaction, or basically heat of reaction, section 5.3, and enthalpies of reaction, calorimetry, SS law, all the way to the food and fuel. You know, wherever we go to Subway, they list the energy content. It's a big thing, all right? For those who are watching weight, you know, sometimes you'll be like, what is the caloric content? We're gonna look it in section 5.9. So 5.1 is the nature of chemical energy. And to start off with, energy is simply defined as the ability to do work, or the capacity to do work. Yeah. And of course, you know, work is force times what in physics? Force times distance give you work. But here, energy is the ability to do work or capacity to do work. I will not just, you know, going details into the energy which exists between two charged particles separated by a given distance. But what I want you to know is the definition of energy. Is a key term, a vocabulary you will see in the exam. I define the term thermodynamics. It is a branch of chemistry which deals with the study of energy and its transformation. It can be transformed from one form to another form. Okay, you will cover in details in Chem 2 thermodynamics. It is chapter 18 in the text. Yeah, we use the same text, which I believe is going to be the same thing. All right. Thermodynamics is chapter 14th edition. I want to make sure that I'm giving you the right information. It is chapter 19 in the text. So we're not going to go in details into that, but for us, chapter 5 is now thermochemistry, which is under thermodynamics, the study of chemical reaction and the energy changes that are involved. What I mean by involved, bear in mind how I define absorb or release. You know, some chemical reaction proceed by absorbing what? Heat from the surrounding, you know, endothermic. We're gonna talk about that. Absorbing heat from the surrounding, endothermic, exothermic. You know, you can recall that. So the changes here is either being given off or being absorbed. So start recalling exothermic, endothermic reaction. Here is just the other, you know, giving us the type of energy which exists between two charged particles. I will not go in details into the electrical energy, but what I want you to have in mind is that we have two important energies to remember. Ke for what? Kinetic energy, which is energy in what? This is energy in motion, energy in motion, energy possessed by moving object. And then there is PE, which you see on the screen. This stands for potential energy. And potential energy is simply stored energy or energy by virtue of position, all right? Stored energy or the energy possessed by virtue of position, this is potential energy, stored energy. The food we consume has stored energy. You know, if you don't eat food, or if we don't eat food, we will gradually get weak and weak and weak because we need what? We need energy to to move around, all right? Energy drinks, you know, to give you energy, to boost you with energy. Or virtue of position, all right? If I hold my iPad pencil, it gets some energy, which if I release, the stored energy will be converted into kinetic energy as it drops on the table or on my laptop. So that is how we define potential energy. The diagram you see on the PowerPoint slide is just electrical energy possessed by two charged particles, which let's forget about that. I'm not going to ask you to calculate the electrical energy, all right, electrostatic energy possessed by charged particles. Now, what is important, which you already or we already covered in the kinetic. Remember in exam one, you had to calculate the kinetic energy, right? Using this equation, I have m v square, I have mv square. This was the equation. We're not going to use that, but I want to relate to this. The SI unit, you know, System International's SI unit of energy is joule, which is J, right? So how do we relate now the unit for a moving object? Meter, this is mass, or here it should be mass in what? Mass in kg. And this is the speed, or sometimes velocity in meters per second. So that when you multiply Crichton numbers, you'll end up with kilogram times meter square per second square, because you are squaring the velocity here, which is the same as 1 joule, same as 1 joule. It's important for, you know, from the previous section, that how do we change that? Now, I don't want to, we will not calculate that. I'm not going to ask you that, but this is important. The equation you see on my whiteboard is important for you, because it will come back again in the final exam. Any question on the definition of energy? I've defined the energy. Why do we need to, why do we need to understand the energy, or why do we have to study the chemical reaction that are accompanied for that, so as to understand how we include the energy in chemical equation? In chapter 3, we balance the equation. In chapter 4, we balance the equation, but we did not have the energy component in the equation. That is where now what is coming in chapter 5. That we'll have to account for the heat given off. We'll have to account for the heat absorbed for that reaction to take place. This heat which is required. If a reaction takes place and heat is given off, we have to account for in the equation, in the balanced equation. That's all about chapter 5. There is the energy component in our equation. And in chapter 5, section 5.2, we are now looking at the first law of thermodynamics. And remember what I said, thermodynamics, it is the study of energy and its transformation. I know it sounds esoteric term that I don't know what it is. You gotta come back again in Chem 2. But what are the first law of thermodynamic states? You may see, I may give you multiple choice on how to define, or if someone asks you, write down or state the first law of thermodynamics, it is simple. You already know. This is the first law of thermodynamic. Energy cannot be created or destroyed. This is the first law of thermodynamic. It's the same. If you want to make your life easier, just say or reconcile with the definition of conservation of matter. Matter cannot be created or destroyed. Conservation of mass. Matter cannot be created or what? Destroyed. That's conservation of mass. So conservation of energy is basically the first law of thermodynamics, which states that energy cannot be created or destroyed. I gave you an example of potential energy by virtue of position using the iPad pencil here that it just, by virtue of raising it to some height above the table, it has potential energy. The potential energy cannot be lost, but once I let it go, once I release it, the stored energy will be converted into kinetic energy, all right, into kinetic energy. As it drops, kinetic energy, potential energy is transformed into kinetic energy. So that is basically the first law of thermodynamics. I don't want to dive into second law and third law. So energy can be converted from one form to another, but it can neither be what? Be created. Even the stored energy in gasoline can be converted into other forms of energy. It can be converted into sound energy from your stereo, mechanical energy in your car. You hear the internal part moving, mechanical energy. The wheels will be spinning as you roll down the street, mechanical energy. The heat energy, if you want to warm your car, all right. Light energy and so forth. So just to give you an idea of first law of thermodynamics, to heat your home, chemical energy is converted to heat. All right, sunlight is converted to chemical energy and many other forms of energy, many other forms of energy. Now, to illustrate the conservation of energy, chemists use an illustration or diagram to define or illustrate energy release and energy what? Energy observed. What I have defined there is the system. I know system can mean so many things. Like I have a radio system, you got a good system, like home theater, some people call it the system. But what do we mean by system with respect to this? What do we mean? If we don't understand this, it will have impact on how you will answer question down the line. Chemists are focused on, let me use this before I really draw a simplified fashion. You are familiar with the reaction flask, right? Where you put your reagent, maybe A plus B, going to C. Where the reaction is taking place is called the system. Inside here, let's say this is what we mean by the system. And the lab, if you are in the lab, right? If you are in the lab, all the four corners, everywhere, is what we call the surrounding. And I can have this as the surrounding right here. Maybe I could have used cream. This is and sometimes they use SRR for surrounding, and the system they use SY for the system. Now, everything here, including the surrounding plus the system here, is what we call the universe. When we say the universe, you may think about the moon, the sun, the stars, the earth, anything. When we say the universe, is everything inclusive. So here is uni equals to what? The system plus the sun. You may see this as this plus SURR. It's the same thing for surrounding. So when I say now this system and surrounding, have this in your mental picture that system is where the reaction is taking place. What surrounds the system is this, it's the surrounding self-explanatory. And then the system plus the surrounding constitute what we call the universe. The universe. That is what we will be looking at. So portion of the universe, when we say now universe, you may think that we are talking about, the galaxy and anything you can think of. I'm talking about the lab, the reaction flask, everything included in there. I don't want you to make it complicated as such, but where we are going to, when we talk about the surrounding and the system, look at the system. That is where the reaction is taking place. If, say, for example, in the reaction between oxygen gas and hydrogen gas to make or to produce water molecule, we call this the system. And then outside, we call that the surrounding. This will be handy understanding that will help us in knowing, or when we get to exothermic and endothermic, that is where we are going with that. There are three types of systems. There are three types of systems. There is you have to know what is, how do you differentiate between the three? There is open system. There is closed and then there is open system, there is closed system. There is open system, closed system, and isolated system. Remember, the system is where the reaction is. This three definition is, you can distinguish between the three of them using these terms, using the mass and energy. Let's see, open system, a region of the universe being started. So a region of the universe being started is the system, by the way. Is the system. We are starting the system. That can exchange heat and mass. And that is why I put these two right here. Heat is in the form of energy. So if I am to write this, I can have an open system. You are losing both so here is losing both. Let me just use the check mark. Both are being lost to the surrounding. Closed system, a region of universe being started that can only exchange heat, but not what? Let me just put this heat. Or I can do this. Let me draw this. Sometimes this can help, And then I have here heat and mass. Can be heat energy and mass. So that this one is lost and this one is lost, depending on how you want to look at. closed system, that means only heat is lost, but not what? Not the mass, it's closed. Here only heat is given off, this is an example, but no mass is lost, not a mass. And then isolated, you know, think of it as isolated, insulated, such as the thermos flask. It's an isolated, it's an insulation. If you put your hot cup in a thermos flask, if it is 24 hours, you put it in the morning, in the afternoon, it will still be hot. If it is 1 liter, still gonna be 1 liter. It's an isolated. So these are the three systems you should be able to distinguish. A region of universe that cannot exchange heat or mass with its surrounding. On my whiteboard, I have a simple diagram, a simple table I can use to configure my mind until commit to my memory, so that if I'm given the definition that how will you define a closed system, for example, a system which exchange this and that, you know, you will have to know, you'll see this in the multiple choice that, you know, you gotta know which one is which. Remember, it's about the what? Exchange of heat and mass. Exchange of heat and mass. Some question can be tricky, you may say tricky, or some can call for critical thinking, Just like, you know, definition of matter. Matter is anything that has mass and occupy full, but there's no way somebody will give you a list of all what? All matter in the world and say, you need to memorize this, so that somebody will ask you, give an example of matter, and then you know, you give them. No, that's not the way it's understanding. So likewise, for all these three systems, if you are given a specific scenario, are you able to classify as open, closed, or isolated? An example is a human being an isolated system, closed system, open system? Think about it. What is it? What is an example? Human body is an example of what? Think of all what we went through, or what I just said, what I just went through in terms of open, close, open, close. Is it an open? Yes, Dylan, to save time, it is open. Somebody might say that, but I'm not losing anything. I'm not losing anything. Why am I open? No. Think of it that an open system loses both heat and what? And mass. If you work out, for example, at some point, you know, you will reduce. That means you lose. All right. Or if you want to try, after dinner, before you go to bed, weigh yourself. When you wake up in the morning, weigh yourself. Chances are it will change, right? What happened? So it's closed system. You got to think through. Thank you, Dylan. Everybody go back again and you know, look at the case scenario. Any question on that? All right. Let's see what we call internal energy. Some of the thermodynamic terms are kicking in now. Internal energy, when we say internal energy, it is the sum of internal is kinetic energy plus potential energy of the system. Kinetic energy plus, yes, Trinity, we are open system because you can lose heat, and at the same time you can lose mass. You know, sometimes due to pandemic, most people, I gained a couple of pounds because of lockdown, and most people gain weight. Now that they are working out, they will lose what? They will lose some weight. So there is loss of mass at some point. That is why we say what? Open system. If you hold an ice cube, you will lose some heat as a result of melting. So there is loss of what? Loss of heat and mass at the same time. We are open system, Trinity, to answer your question. Trinity?
Yes, I was just making sure. I thought that I heard you say something about a closed system and I was just confused.
No, it's not close. It's not close, yeah.
Okay, thank you.
Thank you, yes. So what you see on the PowerPoint slide, internal energy is basically sum of kinetic energy plus potential energy of the system. And chemists use this notation. You'll see E, not for energy, but it stands for internal energy. Internal energy is used. We use E. Don't think that E represent energy. It represents internal energy of the system, which is the sum of kinetic energy and potential energy, Ke plus potential energy. Well, this will help us not, I'll not ask you what is internal energy, but change in internal energy signifies whether heat is being lost or heat is being received. And when we say lost, it has to do with what? The system where we are focusing on. Change, you know, this means delta means change in internal energy, change in internal energy. This means change. You see this quite often. Maybe you have seen this means change. All right, and we have delta E means change in internal energy. How changes this? How changes in internal energy for the system? Which it can be negative, it can be positive. Negative means heat is lost. Negative means heat is lost. Positive means heat is absorbed. Anything greater than zero, you know, when you start, remember the number line? When you have -1, -2, and then 1, if we have 0 here, 2, 3, anything greater than 0 is positive. And positive in relation to exothermic and endothermic, because that's where we are going, means it is getting in. Let me go back to a more simplified system. A plus B, this is where C plus D, this is where the reaction is taking place. This is the system. And then here is the surrounding. So now, if something is getting in, this is positive E. It is being absorbed from the surrounding, just to give you an illustration of what means absorbed from the surrounding. Remember the surrounding? This is the surrounding. It is getting in. And if heat is negative, it is released to the surrounding. It is released to the surrounding, sum of that. So the overall change in potential relate to the endothermic exothermic reaction, endothermic exothermic reaction. Come back to that in 5.3. But in change in internal energy with the sign convention, okay, anything less than that means it is negative. You see this negative means release. I'm using the green arrow to means it's getting out of what? It is getting out of the system. I'm using the yellow highlight here that change in internal energy, if it is positive, it is getting into the system. How do I relate this? You know, when we look at this, the system surrounding, chemists are concerned with the system, not the surrounding. It is the system, not the surrounding. You know why? If, let's say, for example, you want to know if the reaction is, or if you want to measure the temperature of a reaction, there is no way you will suspend the thermometer in the lab and see if heat is being released to the surrounding. Remember, the surrounding is the lab, and say, okay, the temperature of the lab has what? Has increased because the reaction is giving away heat to the surrounding, which is the lab, and then I know it is exothermic. The only way is to measure the temperature of the reaction itself. We are focusing in the system. That's where we have this negative positive thing, because if you stand in the surrounding, that means you're going to be positive and the interpretation will change. So position yourself in the system in order to assign this convention as negative or positive. Negative or positive. These are three quantities for the internal energy. I've just explained the significance of positive and negative. Positive means it is gaining, it is positive coming into the system. When we say gain, it is getting in. The system is gaining from the surrounding. Maybe it is making sense now that I defined before what constitutes the system, what constitutes the surrounding. Other than that, somebody who is not here, they don't study. You know, when I throw in these terms in the exam, you don't know what system is, what surrounding is, and then you talk with change in internal energy, it will take a toll on you. So a negative sign in change in internal energy means the system is losing. Look at this, negative, the system is losing. Some conceptual question is, you know, what does positive means? Or you may be given the numerical value for that. Now, this exchange here, change in internal energy, that means exchange of internal energy between the surrounding and the system, can either be in form of Q, which is now heat. This is something you need to know, heat. This is the notation for heat. Moving forward or in thermodynamic, the symbol Q stand for the heat, which can either be positive or negative. And W is, of course, work. You'll see this work. So that we can rewrite, remember the exchange, the change in internal energy. Change in internal energy can be now Q plus what? Work. Q is the heat and W is the work. Change in internal energy. Change in internal energy. Q is the heat. Remember what that means, heat. Here are some illustration. The yellow bag, I don't know if it's a container inside a safe, is the internal energy here, the system, the internal energy of the system where we are focusing. If heat is gained, that means positive. If heat is absorbed, that means it's positive. If heat is released, That's hot, all right, negative. This might not really, we started off with this might not really, if you can commit this to your memory, I can show you again the same diagram illustration. If this is the system, when it is giving away heat, look at the R, that means it is negative Q. That means heat is given off. And we call this exo. You know what exothermic is? So negative means heat is given off. You are losing. That is how, the first time you look at it, you're like, I thought we are less by something. And the author here is using the number line that, they want you to reconcile with this, that anything less than 0, you see this, anything less than 0, look here, if 0 is, that means negative, negative, negative. I'm using in my diagram here that negative Q, we are losing. We can also, here, if, look at the arrow, negative W, let's work done. This means system is losing work. The significance of this is system is losing work. Negative. You see here, look at the diagram on the PowerPoint slide. The red arrow means it is carrying what? It means system is doing work or is losing work. You will not see in the problems, you will not see the work done or being lost. Or, you may see something like the system is losing work, the system is doing work, or, negative. As opposed to now, this Q positive, and of course we call this endothermic. We call this endothermic. You see that? Endothermic. Then for positive here, positive W, remember this is the system. Positive W means work is done on the system. Work is done on the system. You need to know the sign convention. The sign convention for work, as well as sign convention for Q, which sums up toward the change in internal energy. Work can be positive, can be negative. This might not really click in your mind, but if you can write again in this diagram, you can reproduce, you can have that. It's going to be helpful for you in understanding. In summary, this is the sign convention. If you have in a table like this, I don't know if it might take a while to really, but I like this. I see the diagram. I can reproduce this over and over and understand the sign convention and what it means. Positive Q means heat is gained and it is endothermic. You know that? Means heat is lost. This is exothermic for negative Q. Positive Q, endothermic. Means work is done on the system. You see, this work is done on the system. It is getting into the system. Negative W means work is done by the system. You know, pi and on, it changes the dynamics, how you will calculate. You will fit in the equation, and if you don't know, how to assign the convention, you will have two numerical values in the multiple choice. And if you use the wrong sign convention, it will mess you up. Question from this table 5.1 or from my diagram on the whiteboard in the exam you expect is, what is the sign convention for work done by the system? That's, I'm just giving you an example. If you don't know, you don't know. What is the sign convention by the work done by the surrounding on the system, or work done by the system on the surrounding? It's even get complicated when you have both work and Q at the same time. It will be a challenge for you to really understand. So I'll just make notes on the sign convention. We will look at, some of the, we look at the calculation, how we can calculate change in internal energy. But I've just summarized exothermic, endothermic. Everybody knows what endothermic is. It is absorbed from the surrounding. Look at what is coming over and over, system and the surrounding. This is our system. And then the surrounding is right here. So that's the surrounding, just give you how you define exothermic and endothermic. I know you know endothermic, exothermic. In this illustration, this is the system. Piece of highly reactive potassium in H2O. Potassium in H2O, this is the system. It will give away heat. All right, you see this? It's an example of exothermic reactions, giving away heat to the surrounding. The key term here is exothermic and thermic, endothermic, exothermic. Any question on the sign convention for Q and W? Any question on sign convention for Q and W with respect to surrounding and the system?
Just based on the exchange of heat between the systems, the endo and the exothermic slides that you just had, I see that there is a chemical reaction under both of those. So would we be expected to know, just looking at a chemical reaction, if it's endo or exothermic, or is that something that we're going to do later?
Right here?
Mm-hmm.
No. It's just the other is just giving you balanced equation and just being politically correct. But the point here is understanding what is exothermic. If you look at the diagram, heat, you can see physically that heat is being given up, right?
Right.
So it is not about looking. There is no way you can look like this right here. There is no way you can know whether it is exothermic or endothermic. But in the upcoming section, we will have thermochemical equation. When I say thermochemical equation, it's different from that equation. Thermochemical equation has the heat in the balanced equation, and that is now when you can look and say this is exothermic and endothermic. Hold on to that, and I'll point out to you. I'll explain to you how when you look at an equation, you will know that this is exothermic, this is endothermic. Right now, this doesn't make any sense, and I'll not know, but here it is just illustration of what exothermic is, what endothermic is.
Gotcha. All right, thank you.
Yeah, it's gonna come back down. Now I'm just gonna explain to you the exothermic, endothermic by looking at the equation without even having the diagram. It's gonna be simple. Bring it, make it simple. I'll make it so simple, all right? So I wanted to, let me see if I have time to start, state function and stuff like that. When we say state function, you may think that, is it like the function organized by the state of Florida, or what is going on here when we say the state? Yeah, I know state of Florida or Georgia and stuff like that, but this is not what this is all about. State here is used in thermochemistry with respect to the system. And there are those, all right, condition of the system. Remember, we are still here on the system. A state function here refers to the condition of the system at that particular time, which is independent of, the day before yesterday or in the future. Here is an example of how to understand what this state function means. You can be given, look here, you can be given a specified amount of H2O. Here is our system. Let's look at this. Here is our system, known amount of H2O, 50 grams at 25 degrees Celsius. What this means, how did we end up with this condition, 25? Maybe we started off with 100 degrees Celsius and we bring it down to 25. Maybe it was ice, solid ice at 0 degrees Celsius, and then we had to melt it to 25. It doesn't really matter where we are, where we started. Forget about, the mass for a minute. The mass is 50 at 0 degrees Celsius. The mass is at 100 degrees Celsius, the mass is 50. At 25 degrees Celsius, the mass is, so it doesn't really matter the mass. The point here is look at the temperature, 0 degrees Celsius, 100 degrees Celsius, 25 degrees Celsius. So temperature is a state function because it does not, the current state does not depend on what it was before. All right? It is just like, elevation. If you take the stairs to get to first floor or take the stairs to get to first floor, if you take the elevator, you take the stairs, it doesn't really matter how you get in there. The point is you are at first floor. That's what matters at that point, that if you are to get to first floor, it doesn't really matter how you get in there. So altitude is an example of, state function. Those functions which do not depend or independent of the path. You see here, independent of the path. How did you get there? How did you get to first floor? It doesn't really matter whether you will take the what? The staircase or the elevator. Likewise, to get 25 degrees Celsius or 50 grams of H2O, doesn't really matter whether you melt ice cube at 0 degrees Celsius, melt to 25, or cool down water at 100 degrees Celsius to 25. But the point here is, do you have 25? It doesn't really matter, it's independent. The temperature is one of the state functions. State functions are those they are independent of. So it doesn't really matter how you may want to read more on state function. Here, internal energy, E, is a state function. It doesn't really matter, the condition or the path taken to get there is independent of the path. But what it depends is only the initial and the final. Initially, we were at 0 degrees Celsius, final is 25. Initially, we were at 100 degrees Celsius, final is 25. If we want to achieve this, you see the arrows moving. This is the condition where we want to get to. It is independent on either way we get in there. Or just to mention, what we mean by state function. State function, internal energy is a state function. However, Q and W are not state function. State function. Now, I don't want to start this new fresh PV work. We will start from PV work. We will look at the work component, change in internal energy, we say Q plus W. And PV work, we will talk about this next time, pressure volume work in relation to still what? Change in the internal energy. We have looked at the Q, release, absorb, sign convention. We are now on this part, the work component in internal energy, which I'll start from here this coming Thursday. What I want you to do before I end the session is, please, I will, in the next 5 minutes, I will make the quiz feedback available to you. Please use the feedback to see what you miss and try to understand on your own. If you get stuck, please let me know. I'll schedule a real quick Zoom for you. We can go through your question. That way you will learn out of the mistake. I don't want you to make the same mistake in the upcoming midterm exam. The class is dismissed. Thank you for tuning in this morning. I'll see you again on Thursday. If there is no question,
Thank you.
again on Thursday. Any question? Thank you, Jenna. Thank you, everybody. See you on Thursday. Thank you. The class is dismissed.